And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process, where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity. Every year, the world produces over 1 billion new tires, and just as many worn-out ones end up in landfills. Just imagine, in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of rubbish. But where do these black rings go after they've served their thousands of miles? They don't simply vanish. They pass through fire, steel, and grinding machines to be born a second time. And what's most captivating, we don't even realize that every day we walk on their second life. Stay till the end, because there I'll reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery of automobile tires. Hectares of land buried under mountains of black rubber rings. These are the silent veterans of the roads, which have rolled their thousands of miles and now lie here, seemingly useless to anyone. But this isn't the end of their story. It's merely the beginning of their remarkable reincarnation. We'll trace how these worn, dirty chunks of rubber pass through a series of brutal yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. Americans have learned to give a second life to the overwhelming majority of tires. The recycling rate for old tires in the U.S. currently exceeds 85%. This means that over 250 million tires annually avoid landfill and are sent for rebirth. Part of them are burnt as highly efficient fuel. Part are used in civil engineering, but a significant and ever-growing quantity is transformed into rubber crumb. At this tire graveyard operates a machine resembling a steel Tyrannosaurus. It's an industrial shredder. An enormous loader grabs an entire handful of old tires and tosses them into the steel jaws of this machine. Inside it, with a deafening screech, two massive shafts with thick, sharp hooks rotate. They seize the tires with relentless force and tear them to pieces with an incredible crash. Inside every tire is a steel belt, a robust framework of steel wire. During tearing, this belt is released, transforming into a glittering web of steel threads mixed with rubber chunks. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, enormous magnet enters the game, rotating above the stream of shredded material. Like a fridge magnet, but 1,000,000 times stronger. It extracts all the steel threads from the rubber mass. With grinding and clanging, the steel belt sticks to the magnet and is dumped into a separate container. This steel will then be sent for remelting, whilst our purified rubber continues its journey. But it's still too large. Next stop, the granulator. During this process, another tire component is released, textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need removing. For this, rubber granules pass through a system of vibrating sieves and air separators. Powerful air streams literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have clean but still rather large material. To become stadium surfacing, it needs transforming into crumb. For this, granules are sent for final grinding, often in so-called cracker mills. As a result of this process, we finally obtained what everything started for, rubber crumb. This is a uniform, free-flowing mass resembling black caviar or coarse sand, where each particle size is just a few millimeters. This crumb is carefully sieved to guarantee perfect size uniformity and packed into enormous bags weighing a ton each. Its journey from dirty tire to clean, high-tech raw material is complete. And now, let's transport ourselves to where this black crumb will find its true calling, construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. But for now, they look dreary and lifeless, pressed against the base. For them to stand up and resemble real grass, they need support. And here, a special machine enters the pitch, resembling a large fertilizer spreader. A process called infill begins. First, the machine spreads an even layer of fine, rounded quartz sand across the entire pitch. It's heavy and settles at the very base of the carpet, acting as ballast so the turf doesn't shift. And following the sand, our main hero is poured onto the pitch, black rubber crumb. The machine distributes it just as evenly across the entire surface. And here, the main transformation occurs. It's like running on 1,000,000,000 tiny trampolines. This dramatically reduces the load on athletes' joints and makes falls far safer. The final touch is combing the pitch. A special machine with an enormous brush drives across the turf, carefully mixing sand and rubber crumb and combing them deep down to the very base, forcing every blade of grass to stand perfectly upright. And now, when the work's complete, before us appears a perfectly green, springy, and safe pitch. And none of the players running on it might guess that beneath their feet lie millions of particles from old automobile tires. To create one standard pitch for American football or soccer requires on average between 20,000 and 40,000 old car tires. Just think about it. A single pitch completely devours an entire mountain of rubber waste. And how many such pitches are there in the country? Currently in the U.S., there are over 13,000 artificial turf pitches in schools, colleges, parks, and professional arenas. And now simple maths. If we take even the minimum figure of 20,000 tires per pitch, it turns out that in sports pitch surfacing across the country alone, over 260 million old tires have found their new home. Natural turf is a very finicky thing. It needs constant mowing, watering, fertilizing, and giving it rest. On average, a natural pitch can withstand no more than 20 hours of play per week. And a pitch with artificial turf? It can operate 24 hours a day, 7 days a week in rain and heat. And now about water. One artificial turf pitch can save between 500,000 and 1 million gallons of water annually. That's the amount of water an average family uses over several years. Add to this savings on fertilizers and lawnmower work, and the benefit becomes obvious.